Okay, can everyone hear me all right?
Yep.
All right, great. So this is the fork join thread pool, and I'm doing a help session this morning at 9 a.m. Yash is doing one at 4:30 p.m. So if you missed any information here and want to join Yash's, then I think she's still doing it at 4:30 today. Anyway, so the thread pool, here are the sections we're going to go through. We're going to go through the basics and how to get started, the general thread pool design, and some logistics about the project, and lastly, debugging. And then I'll give you some general advice at the end. So let's talk about how to get started on this project. One member will fork the base repository, and there's the Git link right there. It'll be on the project page too. And just like in the last project, you're going to invite your partner to collaborate on it, give them permissions, and then they'll clone the forked repository. And then once you have it cloned, I think automatically it should be set to private, but just make sure it's set to private anyway in the GitLab settings. This is one of the most important things in systems. If it's not set like this, you could have a potential honor code violation on your hands. So just remember that for all projects, set it to private. So we're going to go into a bit of basics as to how the thread pool works. As you know from the Outfox exercise, a thread is a single sequential flow within a program, and a process can have multiple threads. And you guys already know the API of how to start threads, pthread create, but basically you're able to pass in a function pointer for the thread to be continuously executing. So that's the cool thing about threads. A thread pool, on the other hand, is what's known as a container of idle threads that wait to do work for an external program. You can think of it kind of as a library. So you're going to be making your own threadpool.c file, and it's going to implement a bunch of functions that different pieces of program will call. It's useful for adding concurrency to programs without having to add locking semantics. That's the other fantastic thing about it. And it can act as an API for external programs or clients to use, as I said. Here's a basic illustration of what's going on here. So in your thread pool, if you guys started already, you know that there's going to be different queues. But as tasks arrive, as you call thread pool submit, they're placed in one of the queues. So they're placed in this queue, and then the different thread pool threads will start executing those tasks in the queue. So this is where you come in. We give you a header file to start out with, but you're going to want to create your own threadpool API that external programs will call. So you're going to make, as I said, this threadpool.c file. And in the threadpool.h file, you have all the important functions that you need to implement that all the other external programs will call. And any functions that you do create that are helper functions, not global functions, should be declared static in the file. Here's a list of the functions you have to implement. You have threadpool new, which accepts n number of threads. And you can kind of think about n threads as the number of workers that you're going to be creating. There's threadpool shutdown and destroy. This is the function that gets called whenever your threadpool finishes. You have threadpool submit, which simply submits a task into the thread pool, and that's going to place it into one of the queues. You have future get, which gets a future, and future free. And I'll talk about what a future is in the next slide. And then we have some bullets down here. So you need to read through threadpool.h for the full documentation of how to implement each one of these functions. And not included, of course, are static functions. That'll be your helper functions for the threadpool project. Yeah, so I think the most important thing to get out of this is reading threadpool.h. It'll help you so much understand what functions need to be implemented, and there are some basic comments in there to help you get started. So futures are basically an instance of a task that you must execute. And from a client's perspective, a future is a promise that is returned once they submit a task for work. And I think the analogy I've sort of heard again and again is a future is sort of a receipt. So when you call threadpool submit with a task, it'll return a future. And basically, when the thread pool doesn't have any current work to do, it'll eventually get to this future from one of the queues, whether that be the global queue or the worker queue. And it'll eventually execute the task within this future and store the result. And at some point down the road, the client that's calling your thread pool functions will ask for the future back. So you can kind of think of it as a receipt when you call thread pool submit. So that's the basics of future. And as you can see, there's a couple fields in the struct that you definitely do need, like this, fork join task T, which is a function pointer. And that's what the thread pool is going to run. And then you have your arguments for the function pointer and the result that is to be returned to the client when everything is said and done. And you also might need in this future struct synchronization primitives, whether that be mutexes, semaphores, etc. So anything you want specific to a future should be placed in this future struct. You're able to add as many fields or as less fields as you want inside this struct, which is kind of nice. It's fairly extendable. So you will invoke task as a method. It represents the method passed through thread pool submit. The return value gets stored into the result. And that's what we're talking about here, this fork join task T, which is just simply a function pointer. Okay, so this is a small illustration as to how this works. But basically, we have the client, as I mentioned, which will call the library function thread pool submit. And once it calls that function, it's going to get back a task, which is a future. And this is going to go into the thread pool as well. The future is going to be in the thread pool to be worked on later. And as I said, we have this little receipt, which is the future that is passed back to the client. And then when the client is ready, it'll call future get when it wants the result of that future. And then basically, when this function is called, the worker thread has to return the future. So that function is called, the worker thread will do a bunch of work, and eventually it'll return the result of the future back to the client. So that's the basics as to how the thread pool will work here. These are the hardest components that you need to implement. Okay, so we have the struct thread pool. This is another structure that you need to implement in your program, and it should contain any state you need for the thread pool. And some ideas for that are locks that you need maybe for your global submission queue. And then you need, of course, your global submission queue. Maybe a list of workers. So that would be insanely important as well. And each worker will have its own queue list as well. And then you can have signaling mechanisms, whether that be semaphores or conditional variables. It doesn't really matter. You can pick whatever you want here depending on your design. Anything else you need. Really, this project is super open-ended, so you can add any fields you want to the thread pool struct or the future struct, anything that can help you out with this project. And it doesn't matter to the client what fields you put into your struct, so don't worry about that. You can put anything you want in your struct. Okay, so now we need a way to protect global queue and a shutdown flag, just like exercise 3. So that's why we do need some sort of locking mechanism or signaling mechanism for that. So keep that in mind as you're designing the struct for thread pool. Okay, before I continue on to the next section about general design, does anyone want to ask a specific question about anything I just said? I'll just give it another 10 seconds. So somebody asked me for the global submission queue, would we just use the linked list from previous .h files? So you can use the list.c and the list.h files from the previous project 1, and that'll help immensely with your list constructs. for instance, your global submission queue and your worker submission queues. So um, you're able to use the links list from previous semesters. In fact, previous projects. In fact, for all projects, you're able to use your list.h and list.c files. So that's pretty much given to you. Did that answer your question? Okay, it did. All right. Any other questions before I move on?
Yeah, I have a question.
Uh-huh.
So regardless if we're implementing a work sharing or work stealing, each of the workers has like its own list of tasks. And I understand from the handout we need to do work stealing in this assignment, right?
Yeah, I'll get to that in the next section, but basically the specification says that if you want to do work sharing, the max grade you can get, I think, is a B. So you will be docked significantly if you take the work sharing approach, and that's in the spec. But I'll get to more about the differences between the two in this upcoming section. All right. Any other questions for me right now? All right, with that said, I will move on to the next section. Okay, so let's talk about the thread pool design. So the methodology here is we're going to split up a bunch of tasks among n workers. Again, n is the variable that's going to be passed into your initial thread pool new function. And like I said before, the number of workers is directly equal to the number of threads that are running in your program. And also, this is kind of a difference between exercise 3 and the thread pool project, but you're going to need to create all the threads yourself. In exercise 3, you didn't need to make any threads, but in the thread pool project, you do need to make all your threads yourself and call pthread create. We have internal and external submissions. So the difference between that is an external submission is a submission from the client code. For instance, maybe we have a merge sort program that uses the thread pool library. And when it calls thread pool submit to submit a task, that's known as an external submission whenever the client is making a submission. And those are put into the global queue. An internal submission is a submission that's called from within the thread pool library. So for instance, maybe the thread pool will run a task externally, like it'll be an external submission, it'll eventually run that task, but within the task pointer, function pointer, maybe it'll call thread pool submit again when it's running in your thread pool, and that's known as an internal submission. So that's kind of the difference between the two. And if you guys need me to elaborate on that at the end, if I didn't explain that well, just ask and I'll try to explain it again best I can. Then we have, of course, our work stealing and work sharing approach, which is what we just talked about. And we have a slide on that, so I won't go into too much detail here right now. And then we have work helping, which is also a good thread pool technique to do. Also, no global variables at all. As I mentioned in previous slides, everything should be static, with the exception of thread local variables. And I'll get into that, why that is in a minute here. So yeah, internal versus external task submissions. As I mentioned, external submissions are called externally by the client and they're added to the global queue. Internal submissions is when the thread submits a subtask. And as I said, that's when the thread pool itself is executing a function pointer that inevitably calls thread pool submit. So that's an internal submission, and it'll be added to the local workers queue. So that's what happens when you call thread pool new within the thread pool. You're supposed to add it to the local workers queue. And you can actually figure out whether or not it's an external or an internal submission by using something called thread local storage. And that's something I believe is in one of the lectures, but thread local storage is a very useful construct for this project. And as it said, for thread pool submit, you'll need to distinguish these cases. But how? And as I said, that's with thread local storage. So here's an example program that could really benefit from using a thread pool called merge sort. And the way merge sort works is well, most of you have taken 3114, so you might know the specifics behind this, but you take an array and you split it up, and you call the merge sort function again for each one of these partitions. So you can see where parallelism can be achieved here, because we can sort either side, the left hand and the right hand side, at the same time. So this could be easily done concurrently with a thread pool construct. So we have some example code in here. In the GitLab repository, we have our merge sort.c file, which is one of the testing files that the thread pool will run. And as you can see here, we have an external submission when we call thread pool submit right here. This is called by the client merge sort. And then it points it to a function pointer, merge sort internal parallel, which is an internal function which will be executed by the merge sort once the thread pool is ready to submit that task. So this is done, and then it'll call future get when it's ready to get the answer, and then it'll free the future, shut down the thread pool, and free any other memory it might need. So that's the basics as to how a program may interface with your thread pool. And again, you can change anything you want about the future struct or the thread pool struct, and that won't affect how these programs are run. These programs don't care about what's inside the future struct. So let's talk about merge sort internal parallel. This is the function that's called when we call the thread pool submit function. We need to pass in a function pointer, and this is what the function pointer is. So this is what the thread pool will inevitably execute. And basically, anything here will be an internal submission from the worker thread. And as you can see, we create a future for the left-hand side of the array for the merge sort. And we pass it a memory to the left-hand side of the array. And then as that's going on, as after we submit this to the thread pool, we call merge sort internal parallel on the right-hand side of the array. So you can kind of see the benefit of this, right? So you have multiple threads working on the left-hand side of the array while your program can work on the right-hand side of the array. So you can kind of think of the thread pool submit function as a function that doesn't do really any work. All it does is adds a future to the either the global submission queue or the worker submission queue, and it instantly returns without doing the work immediately. So that gets submitted, and then your program, while it's waiting for this to be completed, can work on the right-hand side of the array. And when it's done merging together the right-hand side of the array, hopefully the other future should be done or close to being done. So when you call future get, hopefully you'll have a receipt ready to go. And that's the benefit of the thread pool. You can essentially do work like 2, 3, 4 times as fast using all of these different constructs, which is really fantastic. So let's talk about work stealing. This is kind of what I was getting at earlier, but the general idea is naive implementations of the thread pool will just have a simple global queue of each tasks and a local deck for each worker. So the main loop of the worker basically says, okay, do I have tasks? If I do, pop it from the front, last in, first out. Okay, so that's the first task. It tries to find if it has work for itself to do. If there's no work in the workers array, then it looks into the global task list. And if there are global tasks, then we want to pop it from the back, first in, first out. And then if anyone else has any other tasks, then we want to pop it back from theirs, first in, first out. This is the work stealing section. So you go through the workers, you look for who might have a bunch of tasks to be completed, and then you pop from the back of their list so that basically your thread pool or one worker doesn't get hogged down with a bunch of tasks. So this will kind of help increase the parallelism in your thread pool. So idle threads spread out the work evenly. That's what I'm kind of getting at. And then each queue and deck has its own synchronization variables. And those are things you can protect with mutexes or semaphores or what have you. So the work sharing approach, we have a single central queue, the global submission queue, which all threads remove tasks from. So if we just have one queue, the drawback is that the queue can become a point of contention, especially when handling small tasks. So work sharing is not the approach you all should use here. Each one of your queues or each one of your workers should have its own submission queue so that the work can be spread across more evenly. So, and of course, in the spec, if you've read, you will get points taken off if you implement purely the work sharing approach. You need to implement work stealing. Okay, and I guess before I move on to design advice, well, actually, let's see how many more slides I have. Okay, I guess we'll do a few more slides and then I'll answer the questions in the chat and so forth. But yeah, you're asked to implement the work stealing thread pool design for better load balancing and lower synchronization requirements. And you have the option, if you so choose, of implementing work sharing for only 80% credit. Definitely don't recommend this option. This is the max credit you can get if you implement this technique. So 80 would be the max. You could get more points taken off. So highly, highly, highly recommend you all do the work stealing approach because we will take off points if you're not. And it's right here in the spec too. Okay, so talk about work helping. In the future get function, you are only able to return the result once a feature is done executing, as I think I've said before. If the task is not completed, you have to think about what you need to do in this situation. So if it's already executed, then you can just simply return the task. But what do we do in the situation where the feature isn't ready? What should the thread do while waiting? The threads should always make the best use of their time, 100% always. You want to minimize the number of threads that are sleeping and maximize the threads executing tasks. So if no threads are executing a task you depend on, do it yourself. Like if you call future get and no other worker is working on that task, just do it yourself. Just pick up the task yourself and start working on it. If a thread is executing the task you depend on, do other work. It may be beneficial to do other tasks instead of waiting. And this will increase parallelism yet again. And then as it's doing other tasks, it'll eventually get to the point where the feature it was waiting on initially will finish. So highly recommend on work helping in the future get function. That'll increase the parallelism in your thread pool project. As I talked about before, we have thread local variables. We want to be able to access your worker queues and possibly locks from within any function, especially during thread pool submit. So this is how we can basically distinguish between external and internal submissions. And as it said here, the naive approach would be to loop through each worker and check pthread self. Thread local storage basically already handles this all outside the box. You just need to make a single statement using the __ thread construct. And then this variable will be different for each thread that has been created using your program. So that's the benefit of using thread local variables. Okay, and before we move on to the next section, I'm gonna answer the question that's in the chat. And if anyone else has questions, just feel free to drop it in the chat, or once I'm done answering this question, just unmute yourself and ask. But Lynn asked, for the main thread, the first thread, it will take a global task and wait at future get until all other threads return their results to future get. Is that correct? When you say main thread, are you talking about the initial thread before you submit any other threads or workers in your thread pool? Okay, he said yes. But basically, for your main thread, you're going to want to. So I'm reluctant to say that it won't be the main thread holding the global queue, because the global queue will in effect be shared by every thread. So your global queue can be stored in your thread pool struct, and that memory will be shared by every single one of your other worker threads. Maybe I misunderstood the question, but does that answer it? Oh wait, maybe there's more to the question. It will take the global task and wait at future get until all other threads return the results to future get. I think you have the right idea here. So global tasks. So basically, what happens is external submissions will go into the global queue, and workers will get tasks off of that global submission queue and work on that and put it in their own worker queues. So essentially, in the long run, when you call future get, the futures will be returned like you say. Okay, so our next question is, how do you distinguish between external and internal tasks when adding tasks into the thread pool submit? That's a good question. So when I create new worker threads, the way I do it is I basically set the worker thread or the thread local variable to equal like the worker that's currently executing the task, or maybe I set it to a certain variable. And when I am executing things externally, that variable won't be set, or maybe it'll be set to null. So it could be a simple check somewhere. You could simply check if this variable is not set or if it's null, and depending on that, you know it's a external submission. So that's what makes the underscore underscore thread so powerful. You can set it per thread, meaning any you basically have the ability of determining which thread is running a certain worker and if it's an external submission. And I believe it's mentioned in the lecture somewhere how to do thread local variables. So don't worry about the implementation of that. It's very simple. It's just a few lines of code. How do you okay, so that I answered that question. If a task running spawns a task, we have to use some kind of thread local storage checker to determine and add it to the local worker queue. Yeah, exactly. So we'll use a thread local storage to determine whether or not the submission is internal or external. And we could do that by checking the thread local storage variable. And maybe we set it to null and initialize it whenever we call our internal function to loop through the work that we have. And so when we set it, we know that for any subsequent functions that we call, that like that the worker that we set using thread local storage will be the same worker for all functions in the same thread. And any external submissions, we can check your worker struct or your thread local storage variable. And depending on what that value is, if it's null, if it's not set, then maybe we have a external submission. So that's kind of how I went about doing it. Liam asks, so if a task running spawns a task, we have to use some kind of, okay, so I already answered that one. For work stealing, are we required to implement load balancing my current naive implementation basically loops through the threads to find one with more than 2 tasks to steal from, which is obviously biased towards threads at the start of the helper array of threads. So I'm reluctant to say that you need to implement load balancing, but what we do test is your speed of the thread pool and your performance. And performance is one of the grading criteria that we look at. So your goal in this project is to make it basically as fast as you can. So in a sense, sure, like it would be a good thing to look into if you could do some load balancing. And the way I sort of do my load balancing in my project is for if I want to steal a job from another worker, I steal the job from the worker with the most amount of tasks. And I'm not sure if that's the best approach, but it definitely helps me out to balance the work between each one of the workers. So you could definitely look into doing something like that. Before I move on to logistics, can I get any more questions, or is that everything for now? Okay, I see another question. I understand what workers should do in the future Git. Workers do not need to wait since there will be some task somewhere in the queue. I am confused for the first thread. This thread is not a worker. Doesn't need to wait at future Git until all other workers finish. So the first thread that's in your program is basically the client thread in a sense. And you're right, it doesn't have any workers. So when you call future Git, when the task isn't done, this is where things get kind of murky. So let's go back to that section real quick, and I'll try to explain this better. But yeah, basically, when future Git is called, if your task hasn't already been executed by any of the worker threads, you need to figure out what to do here. And if it's being run by another task, by another worker, then you basically have to wait until that other worker completes the task, and you should be working on other tasks inside of the thread pool. So that's definitely something you have to look into. But you're in work helping, you are able, even if you don't have your own worker, you are able to look at the other workers in your thread pool, and you are able to look at the global submission queue to do other tasks. So that's something that you have the option of doing. So you're right, it does need a way at future Git. However, you should, if you can, do other tasks, if possible, in your future Git function, if you're currently waiting on your future to be returned. So I hope that answers your question. I'm sorry I didn't explain that too well earlier, but now I fully understand what you're saying. Liam asks again, to what extent is performance accounted in grading? The spec mentions a yardstick, but isn't specific to a point value. That's something I'm also a little unclear about, and I think that's something that we should consult to the GTAs about. But I think it really varies. From what I remember, while performance was a big part in grading last semester, I think as long as you and I think Dr. Bach will make a post on Piazza as to what benchmarks you should get for the thread pool project, and I'll talk to him about that. But basically, there's different criteria in the performance benchmark, and you have to hit like a certain amount of seconds. So I'll talk to Dr. Bach about it, and we'll probably get a table put out there with times you need to hit. And that will sort of determine your performance points. So we'll get on that in the coming weeks. Okay. So any other questions for me before I move on to logistics? Sorry for making everyone wake up at 8 a.m. here. This is the the only time I can really do the info session, unfortunately. I'm still a little sleepy myself, even though I have to wake up every morning at 7 for my other office hours. All right, it doesn't look like there's any other questions, but I'm going to move on to the logistics section. Okay, so number one, and this should come as no surprise to you, but submit code that compiles. The way you can do that is by doing all of your testing and compiling and stuff on our login. And if it compiles there, it's going to compile in our auto grading script. So make sure it compiles. We're going to be testing on our login. Test using the driver before submitting. So there's going to be some scripts in the thread pool repository that we gave you. And make sure you test with those scripts. While grading, each test will be run 3 to 5 times. And if you crash a single time, it's considered failing. Make sure you test your thread pool multiple times. Make sure that there's no race conditions. You can double check all of this with Helgrins or Valgrins or GDB. If there's a single race condition we detect, then we can basically consider your project as not complete. Benchmark times will be the average of the 3 to 5 runs, assuming you pass all of them. Okay, so here is the breakdown of the grading. So we check your Git usage as we've done for previous projects. And if I recall, the last project, I think we made sure you had a few commits in your Git version history. So make sure you have at least 3 to 5 commits in your version history, and make sure you commit as early and often as you can. And you'll have no problem with this, like the easy 10 Git points or however many it is. And then you have your functionality tests to make sure that you actually have your thread pool implemented correctly. And then performance, which is if your thread pool meets the performance standards that we'll post on Piazza. And GTAs will determine the exact breakdown of points. Fortunately, I don't have access to the exact breakdown as I'm just a UTA. So if you guys are curious as to how it will be graded, consult to a GTA, and maybe I'll talk to them myself, and we'll see if we can get a more granular breakdown of how the points are distributed for this project. Performance will break down into rough categories based on real-time scores, and we'll have like a little website that you can check your submission against to see which people have the best thread pools. And don't worry, your information is not going to be on there. It's going to have a secret value associated with your thread pool, and then you can sort of benchmark your thread pool against other people's thread pools. You must pass the basic test before getting anything for performance. There's a flag in the driver that indicates if you meet minimum requirements. So that's pretty self-explanatory. Performance. So as I've said, this is more relative to peers and sample implementations. And as we get more thread pools submitted, we'll have more of an idea as to what those points will be. But for the scoreboard, there's going to be multiple different benchmarks. We have the nqueens test, the merge sort test, the quick sort test. So all of these are different algorithms that'll be run against your thread pool. I would pay attention highly to the number of different submissions on your that your peers have submitted, and you'll see how fast comparatively your thread pool is to the other thread pools. So make sure you keep looking at the scoreboard for ideas as to how your other peers are doing. And then, as I said, benchmarks will be posted later on by Dr. Bach, so that'll be probably posted on Piazza sometime in the future. We have our test driver in the CS3214 folder, and you can pass multiple options to that. -R is the basic tests, and then -T, and then the test name will select one test. And the reason why you would probably want to do one test, first of all, is because it takes a long time to run all the tests. So just keep that in mind. And when you're debugging your code initially, it might just be worthwhile to test it using one of these tests so you're not waiting forever for the test to complete. So just keep that in mind. So that's the test driver. It'll tell you basically if you pass a thread pool. Make sure you run tests multiple times. Race conditions can cause you to crash only 20% of the time. And you can run the driver multiple times. And if your driver runs successfully more than 10 times or more than 20 times or what have you, then you can kind of consider as your code race condition free if it runs successfully for 20 plus times. And we run it multiple times in the driver. But yeah, do make sure you don't have any race conditions in your code because we do take off substantial points for that. As you said, we'll run it multiple times when grading. And all of the tests are C programs compiled against your thread pool. And all of those C files are in the initial Git repository for the thread pool project. So this runs the test 5 times and averages the result. You can pass in different values for B, as I mentioned, maybe 10 or 20, and this will run the tests multiple times. And that will basically, in a nutshell, simulate what we're gonna do for grading. So make sure your test passes multiple times. If it fails even once, like we said, if you think it might fail when we start grading it and it does, then we will take off substantial points for that. So just keep that in mind. Okay, so as I said, there's going to be a scoreboard. We need to change the link for this because it's not summer 2020 anymore, but we'll post a link for that on Piazza and in the chat. You could post your results to the scoreboard by using the script fj post results.py. And then once you run that script, it'll be submitted into the scoreboard, and you can see your other peers in there too. So the current benchmarks we have with all the thread pool projects were done from last semester, and we do have some new hardware in our login nodes. So we will sort of have to adapt our performance for that. And again, Dr. Bach will post on Piazza a rough criteria for what your thread pool should meet. And if you exceed that amount of time in seconds, then you shouldn't lose any performance points. In fact, I do believe that we might give bonus points for submissions that have exceedingly well performance. Okay, before I move on to debugging, I'm going to answer this question. With performance, are we graded compared to our peers? For example, the top 25% get A's and so on. No, that's not the case. I think that would be a little unfair if we did it like that. So basically what we'll do is we'll have a bunch of people submit their thread pools into our scoreboard. And then based on the results we see there, Dr. Bach will come up with a rough criteria for what thread pools should meet, whether that be like 5 seconds for one test, etc. And then he'll post that on Piazza, and basically that'll be the rough cutoff for your performance score. So if I remember correctly, maybe I'm right, but maybe I'm wrong, but I think that most of the people who submitted to the thread pool last semester in spring, like maybe the top 50% or so, or the top 40%, I think they got most of the performance points. So I wouldn't worry about being compared to your peers there. And then Liam says, sounds like being graded compared to peers. Well, so the difference here is that we'll come up with a rough benchmark, maybe a week out. And depending on what those numbers are, if you meet all those numbers, if you revise your thread pool and you meet your numbers, and Dr. Bach will pick reasonable numbers for this, by the way. It won't be like really high numbers that are really hard to attain. But once those numbers are met, then you can safely assume that you won't lose any performance points. So it's less so of being compared to your peers and more so of being compared to the numbers that Dr. Bach picks based on like what we think is an appropriate number for the submissions. So that's kind of how we're gonna do it. Then we have another question. You said like a week out. we will know these numbers. Is it technically to be done earlier because technically project due in like 10 days? That's something I don't know the answer to. That's something I'd have to ask Dr. Bach, but I'll get back to you on that. So that's that. Any other questions for me before I move on? Okay, if no one else has any questions, let's go into debugging tools. So debugging multi-threaded programs can be difficult. You shouldn't just use printf for many reasons. One of the reasons is your code is not going to be sequential. It's all the code is going to run at the same time with multiple threads. So if you run printf, you're basically not really going to know which thread is making that print statement. And again, the kernel or the process can schedule any thread that it wants to. So your printfs are all going to be whack and out of order. Instead of using printf, you should use other techniques like GDB and Helgrind for debugging. Helgrind is a Valgrind tool, and most of you probably have already run into using this with the exercise 3. But basically, you pass in -- tool equals Helgrind into the Valgrind command line, and this will basically tell you where all your deadlocks are and synchronization errors. So please do keep that in mind. That'll be very important for you debugging this application. By the way, I don't know if everyone saw this, but I did make a comprehensive post about how to debug multi-threaded programs on Piazza. So open Piazza and find the POSIX threads debugging tutorial. And I run into how to use each one of these tools. I tell you how to use Helgrind, data race detection, and GDB. I think you also have the capability of using something called thread sanitizer. Personally, I haven't used it in the past, but others have told me that it's been successful in catching bugs in their multi-threaded programs too. So if you're interested in that, I'm sure there's a lot of tutorials online on how to use that. I personally don't know how to use it, but if you come to my office hours, we could probably figure it out together if you ask. But yeah, other than that, highly recommend starting out with Helgrind and DRD and GDB. And if you can't figure out how to use any of those tools, or if your error can't reproduce itself with any of those tools, then maybe try thread sanitizer. So this is something called Wilgrind, and I'm just going to briefly go over this because I think Wilgrind is broken this semester. But in the last semester, we had a tool called Wilgrind, and it might be we might try to repair that this semester if we can containerize it. But basically, this is another thread sanitizing tool, and if we can get it back up and running, then you all will be able to use this to sanitize your threads further. But I'm not sure if this is going to really be in commission this semester. And it's basically a web interface that you upload your thread pool to, and based on that, it'll come out with a bunch of potential errors that your thread pool could be running into. General advice: start early. I know these info sessions are done super late, but you should have at least some code written already. And if you look at your header files, if you haven't started already, that's a great place to start. The thread pool project is not as hard as the other projects, in my opinion. You're only going to be writing maybe maximum of 200 to 300 lines of code. And just to put that in perspective, a lot of outfoxed solutions I've seen have been longer than this. So this is less code than you're writing for the previous project 1. In my opinion, the harder part about this project is not writing the code. It's about debugging. So you really have to get acquainted with GDB, Helgrind, and Valgrind. And it can be difficult and time consuming. Although I will say that in my experience, the debugging problems I had with this project were as time consuming as the debugging problems I had in project 1. So I don't know if that'll make it easier for you guys or harder for you guys. Just make sure you allocate maybe 3 to 5 days just for debugging to make sure you have everything working correctly. Also try different strategies if you want to boost your performance. As I mentioned, all the strategies here should give you enough performance to meet the performance criteria that we have, with the work helping, the work stealing, all that stuff should give you max performance points if you do it correctly. Other than that, that's all the general advice I have for you guys right now. And I will go into chat to see if there are any other questions for now. What does DRD catch beyond Helgrid? DRD is highly optimized to find data races. And if you look at the post I have on Piazza, you can kind of see an example of that, where I have a data race attempting to access a specific variable. But Helgrind and DRD can catch the same errors, but DRD, I believe, is more optimized for data races. Helgrind can catch a lot of generic errors like synchronization problems and deadlocking, locks out of order, and data race detection can detect data races quite efficiently. If one tool doesn't work, try using the other. If both tools don't work, try using GDB. Any other questions for me right now? And feel free to unmute yourself if you want to talk. All right, I'll just give it.
So early, can I ask one question?
Yeah, go for it.
So earlier you mentioned that thread pools are beneficial because it like absolves the user for having to deal with locking mechanisms. Could you expand on that a little bit?
Okay, yeah, so I mentioned that early on. So these example programs don't have to use locking mechanisms, especially for like merge sort, as you can see here, because when you call merge sort on a specific piece of data, your program is only going to be looking at either the left-hand side of the array or the right-hand side of the array at any given time. So no locking mechanisms are required here in your client because it's giving different pieces of data to the different futures, if that makes sense. So the futures will have different pieces of data that they'll look at. So in a nutshell, this will ensure that your thread pool doesn't need to worry about how the data being passed into thread pool is handled.
Because that's the responsibility of like the submitter to deal with to make sure there's no conflicting data being shared in the thread pool.
I believe so, yeah. Any other questions for me? All right, I'll give it just 30 more seconds, but if there's no more questions, I'm going to wrap up here. And I'll post the recording on YouTube, and feel free to attend Yasha's session at 4:30 today. I don't think she's changed her time, so she'll have hers in the afternoon. But yeah, that's all I have to say. Again, feel free to pester me with any questions, and post in the Project 2 chat, and come to our office hours. But yeah, we'll help you out the best we can. Like, you guys are not alone in this project. I know it seems daunting, but the worst part is not writing the code. The worst part is debugging. So again, make sure you familiarize yourself with those techniques. I know some people who have written the whole thread pool project in one day, and this is before debugging, of course, but make sure conceptually, like on a piece of paper or something, you understand what each of the functions are doing. And once you understand the whole thread pool project conceptually, I think it would be pretty easy to write the code for this. It might take you a few days, but when it's all said and done, the thing you have to worry the most about is the debugging part. Also, last pointer, make sure you understand your list functions, just like you did in project 1. Those are going to be really, you're going to use the list functions more so in this project than in project 1. So those will be super important. And so just make sure you have the list.c and list.h files and make sure you utilize them. Okay, and if that's everything, I'm going to wrap up here and I'll save the recording and I'll put it on YouTube. Hopefully we'll get it uploaded today or tomorrow. But thanks everyone for stopping by. Post your questions in the P2 chat if you have anything else you come up with, and one of us will be happy to answer them. So thanks everyone.